So once again, I would like to emphasize that please maintain a separate notebook for calculus, just like you would be maintaining a separate notebook for vectors or structure of atom or any of the other tracks that are going on, right? And jot down rough notes during the lecture, okay, lecture notes which you can review later. Of course, I will be sending you the PDF of the complete whiteboard lecture notes also, but at the same time you should jot down the important points as the lecture is going on, and whatever numerical analysis we are doing, you should do that uh, in that notebook as you're noting down the things also. And of course, from today's lecture onwards, there will also be some assignment and worksheet that we sent to you. So please make sure that you're doing that also systematically in your notebook. Okay. So just as a quick recap of what we learned last time, we saw that in physics, if we define speed as the rate of change of distance with respect to time, then there are two types of speed that we define about. We define average speed as the total distance divided by the total time. So average speed is defined for a time interval. That is, let's say T1 to T2, or we can say that the time interval is equal to T2 minus T1. So this becomes equal to the distance traveled in that time interval divided by the total time interval. So we had seen that the graphical or the geometrical representation of this average speed will become, if this is our distance versus time graph, so let us say that graph something like this. So you can see that it has a variable slope. That means the speed is not constant. Okay. So now suppose this is my time T1 and this is my time T2, and we want to calculate the average speed between these two times. Then we see that we plot this point here, this is S1. And we plot this point here, it is S2. So when we are calculating the average speed as S2 minus S1 upon T2 minus T1, it just becomes the slope of this type of line, which is called a secant line. So we join these 2 points with a straight line. It just becomes the slope of the straight line. You can see that this is our S2 minus S1 distance traveled during this time interval T2 minus T1. So the ratio of these two things is nothing but tan theta. Okay, so this is equal to tan theta, or slope of the secant line drawn
Could
between.
you please explain what is a secant line?
Yeah, explain T1 and T2. So if we join 2 points on this curve, okay, this is our distance versus time curve. So when we join 2 points on this curve, it is called a secant line.
Okay, sir.
So a straight line joining 2 points on that curve. Specifically, these 2 points are at time t equal to t1 and t2. Then such a line is called a secant line. And the slope of that secant line becomes what we call the average speed between those two times. Is clear now, Vita?
Yes, sir.
Okay, very good. Okay. Okay, I'm just going through a couple of messages I've received on the text. So Tanay, you have asked about how to submit the assignment. Yes, so there will be a separate group for homework submission or assignment submission, wherein what you have to do is whatever homework you do in your notebook, you have to take a scan or a image of it and send it to that particular group. Okay, so you will be informed about which group you have to send the homework to. Okay.
Okay.
Sir, group Discord or WhatsApp?
Yeah, Discord also. If you are already on the Discord platform, then you can submit it on that. There is a link for the assignments or homework submission on each of the batches pages. So greenhouse batch, if you go through that Discord server of IITian sub greenhouse, you will see that there are separate pages for example, there's one page where all the subject wise assignments are uploaded, then the subject wise recordings are uploaded, and there's a page on which you can post your doubts. Similarly, there's a page on which you can post the homework or assignment. Okay. Now Tejas is saying that can we say that instantaneous speed is considered as average speed in a very small interval of time? Yeah, that is correct. It is instantaneous speed is what we say rate of change of distance with respect to time, but for a very small interval of time. But the moment we are talking about speed in a very small interval of time, we should not use the term we should not use the term average speed anymore. We should exclusively use the term instantaneous speed. Okay. So
Yes,
instead
I
of
got.
understood, no? So instead of saying that it is average speed for a very small interval of time, we will say it is distance traveled divided by time for a very small interval of time. Okay, so that is the difference between how we will denote average speed and instantaneous speed. Okay. So this point we have already seen last time, the average speed concept and the instantaneous speed concept. We will develop that further today in the exact language of calculus. However, just to revise what we saw last time, let's also see the geometrical definition of instantaneous speed.
Sir?
So instantaneous speed is defined as distance traveled upon time interval, but with a condition that the time interval should be very small. And basically, the smaller the value of the time interval, the more accurate is our measurement of the instantaneous speed. That is what we saw from a practical point of view, that a speedometer or a speed gun, it manages to measure the speed by measuring distance traveled divided by time for a very short interval. So if something is measuring for a microsecond, it's reasonably accurate. But if something is able to measure for a millisecond, it is comparatively less accurate, because millisecond, as you know, is 1,000 times microsecond, like that. Okay. So practically speaking, in terms of measurement, that is how we define the instantaneous speed, that it's distance upon time for a very, very short interval of time. And the shorter the interval of time, the more accurate we can say our measurement of that speed is. Okay. Now, in terms of graphical approach, what we can think about instantaneous speed as an interpretation is somewhat more abstract. Okay. Abstract in the sense that it is something that we can understand intuitively, but we can't really directly develop a formula for it. Like we developed a formula that it is for average, it is S2 minus S1 upon T2 minus T1. So like that, we can't develop a direct formula immediately because it is something more abstract. So let's say this is a particular instant of time, T equal to T, because instantaneous speed is defined at an instant. Okay. It is at an instant. So you want to find instantaneous speed at that particular instant. So what we have to do in terms of the graphical approach is that we have plotted this time on the graph as this point when the distance is s and the time is t. Now we have to basically zoom into the graph as much as possible. Let's say we really zoom in by a comparatively large amount, and we have to see that what is the closest point that we can think about from that one. So let's say according to my graph and according to how much I have magnified, this is the closest possible point that I can draw without getting into too much of trouble drawing. So this time interval from here to here, this time interval becomes delta t, where it's a very small time interval. And correspondingly in that time interval, I can see that should have traveled by a very small distance. So this vertical change is that very small distance during that very small time. Okay. And then what I should try and do is I should try and join these two with a straight line, which is a matter of really judgment, like perspective, whether we are able to do that or not. So as I said, it's an abstract idea. It's that something we can imagine, but not probably perfectly execute, not according to the definition that we have shown so far. Okay. So like that, any instrument which is also measuring instantaneous speed, it is measuring up to a certain level only, because that instrument is able to measure for a certain interval of time, which is as small as it can measure, but not necessarily the smallest interval of time. There might be another instrument that is able to measure for a smaller interval of time, and that one will be more accurate. So anyway, so this type of a line is called a tangent line, because when we zoom out of the graph, then it does not seem like it's passing through 2 points, but it seems like it's just touching the graph at 1 point. So that sort of a line is called a tangent line. Okay. So this becomes the slope of the tangent at t equal to t. Now, what is the tangent? The tangent is a straight line drawn through the point t equal to t and the closest consecutive point.
Sir, that is V, no?
Yes. Which one?
V, slope के बाजू में. It's
V.
V or अच्छा, okay.
This is V, no? This is instantaneous speed. Okay. So instantaneous speed, okay, that V is equal to the slope of this tangent line. Okay. Now, what is a tangent line? It is now the difference between secant line and tangent line. On a graph like this, if I take two separate points altogether and join them with a straight line, that is called a secant line. Whereas at a particular point on the graph, if I have a line that is just touching the graph at that point, so practically how I've drawn that line, I have taken that point and the next consecutive closest point on the graph and joined them with a straight line. Then that one is called a tangent line. Okay. So the accuracy of drawing my tangent line, that is dependent on how close I can draw the second point to the first one. But technically it should be so close that it looks like it's merging with the first one. So it will be 100% accurate, my tangent line, provided the second point is actually merged with the first line. So as I said, it's an abstract idea. Yes, Tejas, that is correct. Atomic clocks can be more accurate. But then the thing is, our instrument has to measure the distance traveled in during that short interval of time. So that is also there. So,
Sir, the speedometers used in the matches, that estimates the time better, right?
the speedometer in what, Bida?
We have seen the speedometer used in the matches, like any of the matches, like baseball.
The speed guns. Right. They are very accurate. Okay. Because they have a system of mapping the moving object like a cricket ball or a baseball or a tennis ball or whatever through a very, very short distance. Okay, through infrared.
So will it give an accurate
Yes,
result?
it gives extremely accurate speed, right?
So,
Yes.
so we can say an average speed, like the time interval is little bit big, and then
Yes.
instantaneous, it is very small.
Yes, yes. In instantaneous, so according to this definition that we've seen of instantaneous speed, in instantaneous speed, the time interval is very, very short. Okay, the shorter the value of the time interval, the more accurate our measurement of instantaneous speed is.
Okay.
So clear so far, no? Okay.
Yes.
Sir,
So-
but if the time period is so short,
Yes.
Sir,
Yeah.
sir, if the when do we call it instantaneous speed? Matlab, if time interval is very short under the limit, so what is that limit?
Yeah, so it's like, see, if we are making a journey which is taking a few minutes at least, okay, maybe even a few hours, then compared to the time of that journey, something like 1 millisecond is a very short interval of time.
Yes.
So you understand, no? So on our graph, on the horizontal axis, typically the divisions in which we have measured like will be at least minutes apart like this, okay, or maybe even more. So compared to those minutes or larger intervals of time, if I take a millisecond or a microsecond even, then that's almost like 2 points which are merging into each other. They're that close.
Okay, so sir, the time limit is dependent on the journey or the
Yeah,
thing
yeah.
to be
It's
applied.
like that also, no? Like, if I'm saying that my journey is taking a few minutes, but then, so I will write my time like this, no? That the time was 6 o'clock and 5 minutes, let's say. Then the next time I would have seen is, okay, T1 was this much. T2 was maybe 6 o'clock and 7 minutes. Then T3 was maybe, 6 o'clock and 10 minutes like this. So now if I'm measuring the distance traveled between these two times, it's a reasonably large amount of time now on the graph. So T1 is here and T2 somewhere here, let's say, and T3 somewhere here. So then this is not a small interval of time. So the distance traveled during this 2 minutes divided by 2 minutes will be the average speed during those 2 minutes. Understood, no?
Yes.
But now let's say my T1 equal to 6 minutes, 6 hours and 5 minutes is over here. Now I plot another time which is like 1 millisecond after this. So then that would be very close to this, no? That would be like almost the next consecutive point on the graph. Okay. So between 6 hours and 5 minutes exactly, and 6 hours and 5 minutes and 1 millisecond. Okay, I will not say it's a large interval of time. No? I will not say what is the average speed between those times. I'll say at that instant only 6 hours and 5 minutes, the instantaneous speed is so much, because during the next microsecond or during the next millisecond, that is going to be the distance traveled upon time.
Okay, sir.
You understood the point now? Okay.
Yes, sir.
So that is from a practical point of view. Of course, we have to come to a more refined definition of this, which will come from basic calculus, okay, which we are getting into today. Okay. But again, a note about this geometrically drawing the tangent. So the point is that if we are drawing a perfect tangent, for a perfectly drawn tangent, okay, the point t equal to t and t plus delta t, where the condition is that delta t is very small, should be extremely close. These 2 points should be extremely close, such that they almost merge with each other. So this becomes the important point, that if it's that close that they merge into a single point, then that is when I can say that my geometrical drawing will be 100% accurate. But I'm not able to see it as two split points. I'm seeing it as one merge point only. Then the tangent line that I've drawn, that will look like a perfectly drawn tangent line. Okay, so even till now the definition is somewhat abstract. Okay, but we are getting closer to what we mean by the difference between tangent line and secant line. What the point now?
Yes, sir.
Okay, very good. Okay.
Yes,
So
sir.
now from this point today, we start our proper understanding of the technicalities of calculus. Okay. So calculus is a branch of maths. One of the things that calculus deals with is rate of change. So the first part of calculus is something called differential calculus. And differential calculus deals with, it is all about rate of change. Okay. The second part of calculus is called integral calculus. We will come to that later. Okay. So before we get into differential calculus, we need to understand what calculus deals with. Okay, like all branches of maths, like we were discussing on the first day, that if you compare physics and maths, physics is a subject that has been derived from natural sciences. That means it has been derived from understanding the physical universe around us, okay, which exists naturally, whether or not we are inventing something within it. Okay, of course, physics deals with invented things also, but it deals with invented things on the basis of laws that are coming from the natural physical universe. So we understand from the natural physical universe things like forces or energies and things like that. And based on those laws and those principles, then we can invent things like machines, etc., using physics. Okay. Whereas mathematics, on the other hand, is not about any natural science at all. Maths is just pure imagination. So from the beginning in maths, the first step, for example, is to define a system of numbers and then to define simple operations based on numbers. So there are so many different types of number systems that you know of: integers, natural numbers, real numbers, whole numbers, etc. But and so many different types of operations that you know of: addition, subtraction, division, multiplication, square root, cube root, whole square, etc. Okay, so maths is all about defining operations for different type of number systems. But there is also another type of thing in maths which is not so much about number systems but about relationships between variables. Okay, and that is called functions and relations. Okay. Similarly, there's set theory also. Set theory also, for example, it creates relationships between different sets of numbers or different sets of values. Okay, so one of the you can say branches of maths which deals with the relationships between two quantities, that is called functions. And calculus is something that applies to functions. So before we get into the principles of calculus, we have to understand what a function is, because calculus deals with functions. So when we talk about rate of change, the question is rate of change of what? So it's not limited to only rate of change of distance with respect to time, which is speed, or rate of change of velocity with respect to time, which is acceleration. It can be rate of change of anything. For example, we could have a situation where the volume of liquid in a container is changing. So there's a rate of change of volume with respect to time. Or we could have a situation where the temperature of this room is changing with respect to time. So there is rate of change of temperature. Okay, or we could have a situation where the electric current flowing through a circuit is variable with respect to time. So there is rate of change of current with respect to time. So it could be any two things which are dependent on each other. So, or any one thing that is dependent on another thing. So it deals with rate of change of a general function. So before we get into what rate of change is in differential calculus, we have to understand what a function is in mathematics. Okay. Can anybody give me an example of a function in maths?
So like that fx and the value of x will change in a particular, like 2x square plus 7x plus
Y
Yes,
is
very
equal
good.
to fx, where
That
y
is an
is
example
the
of a function. Okay, so
dependent
y is
variable.
equal to fx is the notation, but an example of a function would be something like this: y is equal to, what was the function you were saying just now? X square.
Yeah, 2x square minus 7x plus 7 equal.
Okay, so let's say 2x square minus 7x plus 11. This was the function you were telling?
Yes.
Okay, so this is an example of a function, because what it's doing is giving me a relationship between two variables. One variable is x, okay, and another variable is y, and is giving me a relationship between these two, that I know that when the value of x is 0, corresponding value of y is 11. When the value of x is 1, let's say, the corresponding value of y is becoming how much? It's becoming 11 plus 2, that's 13 minus 7. So that's how much?
6.
6. Okay. When the value of x is, for example, -1, you can see the value of y is becoming how much? 2 plus 7 plus 11. So that is 9 plus 11. So that is 20, and so on and so forth. Okay. So this is an example of a function. Okay. So what is a function? Now, one thing specific over here. So we'll come to that. So a function is a relationship. And that relationship, for example, can be given by a maths formula like we have, or a maths equation like we've given over here. Okay, so a function is a relationship between, now in more technical language, we will say an independent variable. Okay, let's say x, and a dependent variable. Now I'll explain why this one is called dependent and that one is called independent. Let's say
So,
y.
sir,
Yes.
is the formula sin theta is equals to 1 upon cosec theta also a function?
No,
Because
that
it
is
in
that is a
relation.
definition of the you can say in that sense that if you think of cosec x as a function, then the definition of that function is that it is 1 upon sin x. So this is a relationship between two functions, cosec x and sin x. You understanding the point?
Yes, sir.
But to define a function itself, we must have two variables in it. One is a dependent variable x and the other is an independent variable y. Okay, so sorry, independent variable x and the dependent variable y. So the general way we denote a function is like this, that y is some kind of relation of x. So for example, if I define y as sin x, or if I define y as x square, or if I define y as, let's say, x cube plus 3x, these are all examples of functions where what is happening on the right hand side, we have some kind of a formula related to the independent variable. So whatever we have on the right hand side, by convention, that is the independent variable. Why it is an independent variable? Because its value will be selected without any dependence on y. Now we will select any value of x independently, but the moment we have selected a particular value of x, the corresponding value of y becomes dependent on it through that rule. So that's why this is the dependent variable. So the convention that we follow in writing a function is the quantity we have written on the left hand side, that is in this case y, that depends on the value of the quantity on the right hand side, which is x. So that is why it is called the dependent variable, because, and this is called the independent variable, because x's value can be selected independent, or you can say independently, whereas y's value.
Sir, it means that whichever variable is there on the left, it can be dependent.
Yes, that will be taken as the dependent variable. So y's value is dependent on the selected value of x.
Sir, we can say like that, no? Okay, f is the function that tells how x is related to y.
Exactly. And fx, this is the relation, or in this case, the more proper word is the function that defines that relationship. It defines the dependence on y on x.
Sir,
Yes.
sir, x value can be selected independently, then y's value will change. So y is dependent. Sir, so here, sir, in the equation y equals to x cube plus 3x, sir, we can also take the value of y independently, and then the
No,
value
so
of
that
x
is the point now. See, as far as a maths equation is concerned, you can do that. There's no problem with that. Like I have written y is equal to x square. So I can select the value of y as 4. And accordingly, x will become how much? Either +2 or -2. There's no problem with that. But here, when I write it like this, as a function, the convention is that x is the independent variable and y is the dependent variable. That means x is such a parameter which is independent, whereas y is a parameter which depends on the value of x.
Okay.
You're understanding the point? Because see, this is going to be used practically in actual physics equations. So for example, if I'm writing velocity as a function of time, So for a moving body, the instantaneous velocity depends on which instant of time we're talking about. It's not the other way around.
Okay.
You're understanding the point now? So it is a matter of this being a specific equation, which is following a convention that whatever quantity we have written on the left hand side, that is the dependent variable, and whatever quantity we are writing of the function on the right hand side, that is the independent variable. Okay, understood the point?
Yes, sir.
Okay. Now, just a matter of general knowledge, this type of function that we've written, y is equal to fx type, it is a single variable function because my dependent variable is depending only on a single independent variable y. Okay, but not all functions in maths are like that. We can have functions of multiple variables also. Okay, so for example, if I'm practically applying this somewhere, the temperature of any point in my room, okay, that will depend on the coordinates of that point, so x, y, z, and that will depend on time now. You're understanding my point? Because the room is a three-dimensional space, so every point in the room has three coordinates, an x coordinate, a y coordinate, and a z coordinate. Plus, at every instant of time, the temperature might be different because of weather conditions. So that would be a very complex function. In that case, the dependent variable, which is temperature, would depend on four other variables, three coordinate variables and one variable of time. So not all functions are single variable functions. In fact, in real life systems, more and more functions are multivariable functions. But here at our 10+2 level, we will study functions in context of only single variable functions. So when we are talking about functions, whether in physics or in maths, even in future in maths in class 12, functions is going to be predominantly single variable functions. So single variable functions means we have only one independent variable. Okay. So only one independent variable. X. So the dependent variable, its value depends on only a single independent variable, which is X. Okay, so hope this point is clear to all of you.
Yes.
Sir, the quadratic function which you wrote on the right hand side,
Yeah.
can we consider that to be a single variable function?
Yes, that is a single variable function, you know,
Okay.
because it has, so the independent variable y is defined in terms of only a single variable x now.
Yes.
Now, whereas if I had something like this now, if I had something like this, that z is equal to 2x squared plus 3y plus 1. Now this is a double variable function. Here what is happening? Z is a function of x and y. So to find out some value of z, I need two independent values of x and y. So when, for example, x is equal to 0 and y is equal to 0, at that point of time, I can say that z's value is 1. Whereas when, let's say x is 1 and z and y is 0, I can say at that point of time, the value of z is becoming how much? It's becoming 3, like that. Okay. But this type of function we won't be studying at the moment. Okay. Because this is a two variable function. This is a type of function we'll be studying at the moment because it's a single variable function. So all these examples I've given you, they are single variable functions.
Okay, sir.
Okay. Now, just before we proceed further, so we have seen that a function is a relationship that we define by some kind of maths expression. Okay, but there is a slight difference between the term relation in maths and the term function. Okay, function is a subset of relation. Okay, Achha, before I proceed, let me answer some questions which have come through the text messages. So, is there any minimum value by which T2 must be far? Achha, you're going back to average rate of change. No, it is more like an idea rather than like giving an exact value. No, it is more about an idea. So in general, T1 and T2 should be reasonably far away. Then we can say that it is average speed. Whereas if T2 comes very close to T1, such that it's almost merging with T1, then it becomes instantaneous speed. Okay. Then also Tejas has asked, a ball falling from a height, its velocity is a function of time. Yes, that's a very good example of a practical application of functions. Okay, so whether you look at a falling ball's displacement or its height with respect to the ground, or even its instantaneous value, its instantaneous velocity, these would all be different functions of time. Yeah. So now coming back to
Sir,
this, that yes.
sir, in the single variable functions, can the independent variable be y rather than x?
Yeah, I mean, it's just a matter of the name. No? So for example, if I write in this way, that for example, if I've written S is equal to 2t plus tq. Now this is an example where S is a function of t. So t is most probably going to be time. Okay. So if we assume t is time, then this time is the independent variable. And S, if we assume, is distance, that is the dependent variable. Okay. Now, similarly, I can have a situation where I've defined, x as a function of y. But the important thing is now x is on the left hand side. So x now becomes the dependent variable. And the relation of x with respect to y. So some kind of formula related to y is on the right hand side. So y becomes the dependent variable. Okay, so that can always happen. But the convention is like when we are just talking about general functions, then by default, we always take x as the independent variable and we take y as the dependent variable. When we apply functions in physics, then y could be anything else like velocity, force, displacement. It could be electric field. It could be so many other things. It could be density. It could be electrical resistance. It could be electrical current. Whereas x could be anything else. It could be time. It could be charge. So many different things it can be. So one variable depending on another variable is just written in this form.
Sir,
Okay,
so
yeah.
in the equation y is equal to x square, which is the dependent and independent variable.
When I write the equation like this, y is equal to x square, what I have written on the left hand side?
Y.
So that is the dependent variable. What I've written on the right hand side with the as an equation, it is x's function. No? It is a relationship related to x. It's square of x. So that means x is the independent variable. Is it clear?
Yes.
Okay. Now you might ask why I'm not writing like this, that x square is equal to y, because that is the convention. Okay, whatever I have to write on left hand side, that has to be the dependent variable, and whatever formula I write on the right hand side, that formula has a variable, and that variable is nothing but the independent variable. So you understood the difference, huh?
Yes.
Yes, sir.
As a maths equation, there's nothing wrong with saying that x square is equal to y. But then this does not represent a function where y is the dependent variable and x is the independent variable. It just represents this relation. Whereas the moment I write it like this, now in the convention of functions, this is a dependent variable defined in terms of the independent variable of x. Okay.
Yes, sir.
Okay.
Sir, what if the value which we have taken for any variable changes, like it is not constant for the equation?
And that is what happens. Now, the value of the variable is not constant. Only at a specific value, we get a specific value of the dependent variable. So if I'm saying, for example, y is equal to square root of x, okay, then x can be 0, x can be 1, x can be 1.2, x can be 100. Okay, and accordingly, I'll get a dependent variable of value of y. So what the relation tells us, or what the function tells us, that when x's value is 0, y's value is 0. When x's value is 1, y's value is also 1. When x's value is, for example, 1.2, y will be square root of 1.2, which will be very close to 1.1. Understood the point? No?
Yes.
Okay. This one, for example, also tells us that if x's value is taken as -1, y is not defined only. So even that can happen in a function. It may so happen that a particular independent variable value does not give us any value for the dependent variable because the function is defined in that way. Or if I have the function, for example, y is equal to 1 by x. Now here for x equal to 0, again y is undefined. Okay, because division by 0 is an undefined operation. Okay, so hope this point is clear. Okay, now just one thing we have to understand, that a function cannot imply multiple values of y for a single value of x. Okay. So for example, if I write the relation that y square is equal to 2x, okay, this is not a function. Okay, because what this would indicate is that for x equal to any value, so for example, let's take x equal to 2. Okay, y square would become equal to 4. That means y square minus 4 would be 0. So that means y could be 2 or y could be minus 2. So this is not allowed for a function. Okay, this is a relation. Okay, it is a relation between x and y, but it is not a function. Now, why it is not a function? Because of this reason, because a single value of x must give a unique value of y. Okay. So for a relation to be a function, a single value of x must imply a unique value of y. This is an important point about a function. Okay, of course the reverse can happen. Okay, the value of y can repeat for multiple values of x. Okay, that is not the same thing. Okay,
Sir,
yes,
so if we have our function as y is equal to square root of 4, so that will only be positive too, right?
yes, that's the difference between the two. So see, y square is equal to 2x actually implies that y's value is plus minus of square root of 2x. So this is not a function. But instead of this, if we had written y is equal to root 2x, this is a function. Or if we had written y is equal to minus root 2x also separately, this is also a function. At the moment we are writing plus minus root 2x, it's not a function, because every value of x, or there are values of x which are giving me multiple values of y. X
Yes, sir.
equal to 0, for example, will still give you a unique value of y, but that's not good enough. X equal to 1 or x equal to 2 or any other value of x, any non-zero value, any positive value of x is giving me 2 values of y. So it is not a function.
Yes,
Okay,
sir.
is this point clear?
Yes, sir.
So,
Yes.
so we can see on the left hand side, it just depends on the power. Like since it was y square, so we could
Exactly.
to
Correct. It should not be expressed
answer.
as a power. That's one way of saying, yeah.
Okay, sir.
Okay. Okay. Now let's understand.
Sir,
Yes.
sir, can you once scroll up?
Okay.
So sir, y is equal to root 2x is a function, but y square is equal to 2x is not.
Y is equal to root 2x is a function, but y equal to plus minus root 2x is not a function. Understood the point? This one is not a function, but these two are independently functions. Is it clear? Okay. Now next thing, let's understand geometrical representation of functions, or what we call graph of a function. So this is also something pretty normal that you're familiar with. Only thing is whenever we are drawing the graph of a function, we have to follow a convention that the vertical axis is always the dependent variable and the horizontal axis is always the independent variable. Okay, we should never reverse those two. Always in the horizontal axis, there should be the independent variable. Whereas on the vertical axis, there should be the dependent variable. So this is for the function y equal to fx. And if I take certain values of x, like this, and corresponding values of y, so they come out to be y1, y2 for each value of x. So these points will all be plotted in the xy space. So these ordered pairs will all get plotted as points. And the smooth curve that we can achieve by joining them together, that would be the graph of the function. So again, the graph of the function's accuracy depends on the number of points I've plotted. The more the number of points I've plotted, the more accurate the drawing of the graph will be. So in an ideal world, if we want the most accurate possible graph, then what we should do is we should write a computer program that will actually plot literally infinite number of points. So the graph is actually, we don't have to draw the curve anymore. It is a collection of one point or the other after the other. Okay. So anyway, here our purpose is not to draw 100% accurate graphs. Our purpose is just to understand the function's behavior by making an approximate graph. So this is how we draw an approximate graph. We draw a convenient number of points and then we join them with the smoothest possible curve. So that curve represents the function. But technically, what does the curve or the graph of a function represents? Okay, the graph of a function is a curve that represents every point in the xy plane that satisfies this relationship, that y is equal to fx. So the graph of a function is a curve on the xy plane such that every point on that curve, x comma y on it, satisfies the relation y is equal to fx, because that is the function. Okay. So for example, if we are having s as a function of t, then it should always be that s is on the vertical axis, t is on the horizontal axis, and every point on the graph satisfies this relation, that s is equal to ft. Okay. So that is the technical definition of what a graph of a function is. Okay. So just make a quick note of this, then we'll discuss further.
So
Yes. Yes.
So where you wrote y equals to root x, like scroll up.
Yeah.
So here we could also write root x equals to 1. That could be a function or no?
Sorry, root x equals to
pi, like opposite.
No, see, if we are writing it like this, root x equal to y, then this has to be expressed in this way actually, that whatever is on the left hand side, it is the dependent variable, no?
Yes.
And whatever is on the right hand side, it's the independent variable. So it has to be expressed as x is equal to y square.
Okay.
Okay, and there's a difference between this and this, no? You understand, no? Because here x is only defined for non-negative values of y, but in the second one, x is defined for all values of y, negative and positive. So they are not one and the same.
Yes.
You understood the point?
Yes, sir.
So maths wise, I mean, just in terms of equation, there is no difference between y is equal to root x and root x equal to y. But when we write the equation in this form, that y is equal to root x, then we are writing it in the language of functions, where the convention is very clear that y is the dependent variable, x is the independent variable, and how y depends on x, that y's value is equal to square root of whatever x's value is.
Yes,
Sir,
Yeah.
sir, I have not understood this last part. What you have written? This
Which
x
last
square,
part?
sir, y square equals to 2x. This
Y square equals to 2x. Yeah.
This one.
So look at this equation, y square equal to 2x. What it means as the relationship between x and y, that y is plus minus of root 2x, no?
Yes, sir.
If I take the value of x as 2, for example, y's value can be plus or minus of 2.
Yes, sir.
Because y square is 4. Got the point now?
Yes, sir.
So this is the same thing now, which I've done over here. See, I've shown you in this calculation, I've shown you the exact reason why this is not a function. Because any value of x, any non-negative value of x will give you a value of y, but positive values of x will give 2 values of y. What the point? So that is not allowed for a function. By definition, a function is which type of relationship? It's a type of relationship that must give us a unique value of y for every value of x.
Okay.
Okay, now definition of graph is clear, I hope, to all of you.
Yes, sir.
So graph is like a normal graph that you are used to plotting at physics experiment levels and all that also. But the only thing is that you have to follow the convention in case of function, that the dependent variable is on the vertical axis and the independent variable is on the horizontal axis. Okay. So for example, okay, this can be the graph of a function. Okay. This can also be the graph of a function. Values of y are repeating, but that's not a problem because they're repeating at different values of x. So this is also a function. I mean, this graph also represents a function. But if I have a graph which is something like this now, the graph is like this. Now, this is not a function. Why? Because you can see a single value of x is giving us multiple values of y. So this is not a functions graph. Okay. It can still represent some relation, but it's not a function. Okay. So for example, when you have the graph of y square is equal to x, like we were discussing earlier, that graph is like this. So each value of x gives you 2 values of y other than 0, which gives a single value. So for example, x equal to 1 gives you plus minus 1. X equal to 2 gives you plus minus 1.4. Okay, so this is not a function. So this graph does not represent a function because this relation itself does not represent a function.
Over here, the independent variable would be y or x.
No, it will not be, no, because see how we've written it now. We've written y square on the left hand side. You're understanding the point? We have to follow a convention, no?
So can you please explain the difference between these graphs again?
See, in this graph, what is happening in the third one, for any particular value of x, I'm getting different values of y, no? Is that happening in these two graphs? No, no. See, any value of x is giving me a unique value of y. Are you following this, beta?
So, but then in the second graph, we have multiple values of x for one specific value of y.
अरे so वही तो उल्टा हो गया ना. See, one value of x is giving only one value of y. The value of y is repeating for more than one value of x. But that is not my concern. My concern is that for a particular value of x, I should get a unique value of y.
Okay, so the value of y cannot be like
The value of y should not be repeated. I mean, the value for a single value of x, I should not get multiple values of y.
Okay.
Now think
So
of this
is that-
practically, na? Think
so
of
how
this
is that like,
Wait a minute, beta. Think of this practically, if this is distance versus time, okay. Now, is this logically possible that at the same instant of time, my object is covering three different distances? It's not
No.
possible, no? Okay. But for
Time
example,
can't also be taken back.
can't be taken back, but that's distance. Okay. Now let's talk about velocity versus time. Now my velocity might first increase, then again decrease, then again increase. So at three different times, my velocity might be the same value. No, that's no problem. Okay, but can my velocity at a particular instant of time have three different values or two different values?
No.
Is that logical? No. At an instant of time, a moving object will only have a particular value of instantaneous velocity. No? It cannot have multiple values of instantaneous velocity.
Okay, sure.
So now you understood the difference between the second graph and the third graph.
Yes, sir.
Yes, any other question? Somebody was saying something? So again, see here.
Sir?
What?
So then we have a rule that for a specific value of x, you cannot have multiple values of y.
Exactly. That rule is what I've showed you over here. No? This rule I've made you note down here. No?
Yes, yes.
Okay. This rule over here. Okay. A function cannot imply multiple values of y for a single value of x. Okay. For a relation to be a function, same thing. For a relation to be a function, a single value of x must imply a unique value of y. Okay, so this is a foundation that we have on relation to be function. Is it clear, beta?
Yes, that's clear now. Thank you.
Okay.
Sir?
Yes. Yes, tell me, beta.
Sir, this fourth graph I have not understood. Can you explain me?
Sorry, this?
Fourth graph. Fourth example. Y square equals to x. This is relation cannot represent a function. Why is that?
Exactly. See the graph, no? For any value of x, I'm getting two values of y. So till now, what we've been discussing, for a given value of x, we must get a unique value of y, no?
Yes, sir.
तो अभी इसमें देखो क्या हो रहा है, सब्स्टिट्यूट करके देखो, x का वैल्यू 2 सब्स्टिट्यूट करो. What is the equation we are getting? That y square is equal to 2. That means y is plus minus root 2, no? That's what the graph is also showing you. It is plus minus 1.4.
सर नहीं समझा सर. एक और मतलब सर आपने यहाँ पे ग्राफ जैसे बनाया सी शेप में, तो अगर हम लोग देखेंगे तो सर इधर से और कोई भी एक पॉइंट को पकड़ेंगे तो वो एक्स और वाई की एक यूनिक वैल्यू तो होगी ना.
क्या बेटा, व्हाट यू आर टॉकिंग अबाउट? ग्राफ का शेप देखो ना कैसा है. ग्राफ का शेप ऐसा है, तो कोई भी x का वैल्यू पकड़ोगे तो ये है ना, ये जैसे x इक्वल टू 4 है सपोज, तो कॉरेस्पॉन्डिंगली ग्राफ को कितने जगह कट कर रहा है? बताओ कितने जगह कट कर रहा है?
दो जगह.
हाँ,
दो
जगह कट कर रहा है ना. तो फंक्शन में ऐसा हो सकता है?
अच्छा, ओके. नहीं हाँ समझा सर, ये मैंने ध्यान नहीं दिया.
हाँ, ओके. बट अगर मैंने उल्टा लिखा होता, एक मिनट, अगर मैंने उल्टा लिखा होता दैट y इज इक्वल टू x स्क्वायर, अभी इसका ग्राफ देखो कैसा है. इसका ग्राफ ऐसा है. So if I take x equal to 1, it only gives me one particular value, na, that y is equal to 1. If I take x equal to 2, it gives me only one value of y, which is 4. Okay. Of course, if I take x equal to -2 also, it gives me the value of y as 4. But मुझे उससे कोई problem ही नहीं है. Because in my definition of function, what should happen? For a single value of x, I should get a unique value of y. So that is satisfied here. So this is a function. But see the difference of this one with respect to this graph. What is happening here? For a single value of x, I'm getting more than one value of y. So this is not a function. Is it clear now, finally?
Yes, sir.
Anything else, anybody?
Yes, sir. Yes, sir.
Okay.
Sir, so
Sir.
which type of graphs are called parabolas?
Yeah, that will come to later. The technical name given to these type of graphs is parabolas. Okay. Any quadratic curves graph is called a parabola in general. Okay.
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 So,
Now,
if we have to identify that a given like equation is a function or not, then we'll have to plot the graph and check, or can we look at it and tell whether it's a function or not?
you can do both. No? If some mathematical relation is given, then from that also you can check that for any value of x, the value of y should not be multiple. Or if the graph of that function is known, or the graph of that relation is known, you can just draw a vertical line and see if it is cutting at multiple places or at a single place.
Okay.
Understood the point now?
Yes, sir.
Okay. So see, there are two ways of analyzing any relation. Now, one is algebraic from the formula of the relation, and the other is geometrical from the graph of it. So from both the interpretations, we can tell whether a given relation is a function or not. Okay, now let's come to the next concept, which is average rate of change of a function. So the whole business of rate of change is the main part of what we have to learn with calculus. So average rate of change of a function So what do we mean by this term? We mean the rate of change of y with respect to x for an interval of x. Okay, so this is the rate of change of y, that is a dependent variable, with respect to x, which is the independent variable, for a given interval of x, that is delta x equal to x2 minus x1, or we can say that x equal to x1 to x2. So how this average rate of change is defined? The average rate of change equals to delta y, that is a change in y, upon delta x, that is a change in x, for this particular interval. So y2 minus y1 upon x2 minus x1. So further, what is y2? It is the value of the function at the point x2. What is y1? It is the value of the function at the point x1. So this becomes the formula for average rate of change. With this last thing that I've written, this becomes the formula for the average rate of change for the function y is equal to fx from the point x1 to the point x2. Okay. This is the notation we'll use, delta y by delta x, and how we calculate delta y by delta x by substituting y2 minus y1 as the value of the function at x2 minus the value of the function at x1 and dividing it by the change in x, that is x2 minus x1. So let's understand this with a quick example. So for example, my function is, let us say, x square plus x, and I want to calculate, find the average rate of change for this function from, let's say, x equal to 1 to x equal to 2. So what I will do is, the moment I'm seeing this is my function, okay, to understand the function is given by this relation x square plus x, and the moment I'm seeing this is my interval, I'll take x1 equal to 1 and x2 equal to 2, and I'll now calculate delta y by delta x. So that is what it is, y2 minus y1 upon x2 minus x1 Now, what is y2 over here? It is the value of the function at x2. What is y1? It is the value of the function at x1. Okay. So now you can tell me here that what should be the value of y1? It is f of x1. So that is the value of the function at x equal to 1. So substitute x as 1. So it is 1 square plus 1. So it is 2. Okay. Similarly, what if I take x2 as 2? What is y2? It is f of x2. Is nothing but the value of the function at x equal to 2. So how much that is according to the relation given? It is
6.
Yeah. So it is 6. Okay. So now for this interval, delta y by delta x will become y2 minus y1, so that is 6 minus 2 divided by x2 minus x1, that is 2 minus 1, so it will become 4. So delta y by delta x will be equal to 4, but this is for the interval x equal to 1 to. Okay, so this is the definition of average rate of change, and now this is an example in how we actually calculate this. Okay. So note this down carefully. Okay, and for the same function also calculate average rate of change from x equal to 2 to x equal to 3. So just like I've done from 1 to 2, similarly you do a calculation from 2 to 3. But
Function is
first,
same, right?
yes, make a note down of this definition of average rate of change properly first. Okay, definition and formula. So as always, here we use the symbol delta for change. Okay. So delta y is the change in y. Delta x is the change in x. So the symbol delta is generally used in calculus for change.
So can you zoom in on the top? So can you zoom in? Sir, what is the unit for rate of change of function?
And then done.
Okay, I will come to what is unit of rate of change also. Okay, at this point of time, it's not important because X and Y are just numbers. Okay, but unit of rate of change will be whatever the unit of Y is divided by whatever the unit of X is.
Okay.
Okay. So anyhow, let's look at the second part of the same question. So here we will take x1 as 2. So y1 will be f of x1. So that is f of 2, which we've already seen above, is 6. But we'll take x2 as 3. So y2 will be f of 3, which is how much? 3 square plus 3. So that's 9 plus 3, right? So that's 12. So delta y by delta x will become 12 minus 6 upon 3 minus 2. So that will become 6. Okay. So this becomes the value of delta y by delta x for x equal to 2 to 3.
So then these values will not have any SI unit, right? Because it's a ratio.
In this case, we are just assuming x and y are numbers. So it's a unitless quantity. Okay. But for example, if I was writing s as a function of time and s is in meters and t is in seconds, then delta s by delta t would be in meters per second. What it?
Okay, sir.
Sir,
Yes.
sir, could you just send the notes on the WhatsApp group?
What happened?
Sir, I have not drawn all these graphs and somewhat part has been missed by me.
It's okay. I'll be sending the notes anyway. Okay.
Okay, sir.
Okay.
Will you forward the recording as well?
Yes. Every lecture we'll be giving you the recording as well as the notes, beta. Just like the first lecture, na? So every lecture I'll be forwarding the recording as well as the notes. Only it takes some time because the files have to be processed. So by the end of the day, it will be forwarded to you. Okay, so next thing, let's look at average rate of change. In the graph of a function. So just now we've seen that how we define average rate of change. We define it as y2 minus y1 upon x2 minus x1, which further we get by substituting the value of x as x2 to get y2 and x as x1 to get y1. So this becomes the ultimate formula for it. Now let's see Okay, what this means in terms of the graph. So I'm sure all of you understood what it means in the graph. It is nothing but the slope of the secant line. Okay. So if we represent the function with its corresponding graph, so this curve represents the function y equal to fx. And let's say this point on the x-axis represents x1, and this point on the x-axis represents x2. Then correspondingly, this point on the graph, it represents x1, y1. Its y coordinate represents y1. Okay. And correspondingly, this point, it represents the ordered pair x2, y2. Its y coordinate represents y2. So once again, you can see it's very simple that the straight line joining these two distinct points, x1, y1 and x2, y2, that straight line slope is nothing but the average rate of change between these 2 points. So such a straight line, as we've discussed earlier, is called the secant line. So what we talked about average speed is now extended to average rate of change. Okay, so this quantity geometrically or in terms of graph, what it means is that it is the slope of the secant line, okay, which is the line joining x1, y1 and x2, y2, these 2 points. Okay.
Sir, so we can calculate it by either, means by calculating tan theta or by calculating it by y2 minus y1 upon x2.
Yes, yes, exactly. So if we have the formula of the function, we can use this formula for average rate of change, y2 minus y1 upon x2 minus x1. If we have the graph of the function, then we have to actually plot these 2 points, join them with a straight line and find the slope of that straight line as tan theta.
Okay, sir.
Yeah, Yashovardhan, to answer your question, the curve is just called the graph of the function. Okay, so that was all about average rate of change. Now let us move on to the more important quantity called instantaneous rate of change. Okay. For a function y is equal to fx. At a point x equal to x, instead of for an interval x1 to x2, it is defined for a point x equal to x. Okay, so now we come to the proper calculus definition of instantaneous rate of change. So it is given by a special symbol which you might have seen. This is given by the symbol dy by dx. So this symbol itself, it is the symbol for instantaneous rate of change. Of y with respect to x. This is a symbol for it. Okay. Okay. Now, what is its definition? Its definition is delta y by delta x, but with the special condition, and that special condition is now called a limit, that delta x is tending to 0. Okay. So this condition So this is read as change in x, that is delta x, tends to 0. That means delta x is so small, delta x is extremely small, such that it's almost 0. That is the meaning of saying that it tends to 0. Okay. So again, how that will be interpreted is delta y will be f of x plus delta x minus fx, okay, divided by delta x. But for the limit that delta x tends to 0.
So in this equation, d is constant, right?
No, d stands for change. Okay. Okay. So
the delta is represented by d now.
Yeah, but under the condition that it's a very small change. So what is dx? It is an extremely small change in x. Okay. So it's basically delta x such that delta x tends to 0.
So, and representing change in the form of dy by dx is not applicable for average rate of change of a function.
No, it is not applicable for average. So that is the difference
not
between
applicable there here.
Yeah, that is the difference between saying delta y by delta x. Okay. So what is this? This is average
That's
rate of
instantaneous, like.
Okay. Whereas dy by dx, what is it? It is instantaneous rate of change. Understood? No? So two different symbols we are using for the two different types of rate of change. Now what I've written on the right hand side, this is the definition of dy by dx. But what dy by dx itself is, it is instantaneous rate of change. Okay, just write down this definition. As we take examples, this will be more clear.
So this will only be when limit is 0, right?
Limit delta x is tending to 0. Yes.
Okay.
So
limit means delta x, sir.
No, limit means it's a condition. Okay, the term limit in maths means that it's a condition. It is a condition that delta x is tending to 0. So what does that condition mean? I've written down for you here below. This condition that delta x tends to 0 means that delta x is extremely small, such that it's almost equal to 0. That's the meaning of tending to 0.
Okay, sir.
So normally, how small of a value do we go to if you're saying that delta x tends to 0?
So that's the thing, no? It's limitless how small it is. It's tending to 0. So that's how we'll see that differential calculus will give us a new method in mathematics to make this calculation when delta x is tending to 0. So it's so small that we cannot say how small it is.
Okay.
You understand? Like infinity is something so large that we cannot define it by a number, no? So like that, tending to 0 is so small that we cannot define it by some number.
Okay. Okay. Like can we say like it's 10 to the power negative 50, or like
So I
even
will
smaller?
say that if you say 10 raised by minus 50, that's also a finite defined number, no? So it should be like infinitely small compared to that also.
Okay. Okay.
So sir, if the limit was extending from if x was tending from till infinite, so it would be a comparably very big number.
Can you speak a little bit louder, but I'm not able to hear you.
Okay, sir. 1 second.
Yeah. Just speak closer to the microphone of your device. Yeah.
Sir, now can you hear me?
Yeah, I can.
So sir, if now the limits was like extending to infinite, so it would be a comparably large number, no?
No, infinite is not large. Infinite is infinitely large. It is so large that it cannot be compared to any other number. You understanding? In mathematics, infinity is very different to just large. large can be 10 raised power 10 also, large can be 10 raised power 20 also, but infinite is so large that you cannot compare it. Got my point?
Okay, sir.
Okay, just write this down. We'll discuss with an example. It will become clear.
Done, sir.
Okay, so let's see how we can implement this. Okay, so even now, you can think, you can see that it's an idea, it's an abstract idea, that I'm saying that delta x is tending to 0. That means it is so close to 0 that we cannot imagine. Like just now somebody suggested that is it 10 raised power minus 50. Now even 10 raised power minus 50, you can imagine how small a number it is. But even then I'll say it is not tending to 0, because we can at least write the number 10 raised power minus 50. No? But delta x tending to 0 means it's so small that we cannot write it. Practically speaking, it's as good as 0. Okay, so it's a very abstract idea. So let's understand how we'll implement this now. Okay.
Sir, what you have written in this right hand side corner?
Doesn't matter, beta. I was just explaining some point to somebody else. Okay, it's instantaneous rate of change, and this is average rate of change. The difference between delta y by delta x and dy by dx. Okay. Okay, so let's look at this with an example. So suppose I have y is equal to x cube, okay, and I want to find instantaneous rate of change. Dy by dx. How will I do that? Okay, so I'll apply the definition. So what is the definition of instantaneous rate of change? It is solved by a certain limit, okay, or a condition. So from now, I'll write this in short form. Limit is LIM. Okay, it is this thing. Okay, where the function which I'm talking about is which one? The function is x cube. Okay, now let's take a couple of examples to understand this. Okay, now can you think of some small value of delta x, but not so small that I cannot write it? Just suggest some value.
10 raised to minus 3.
Sorry, x raised power, I mean 10 raised power
minus 3.
Minus 3. Okay, so let's take this as 0.001 or 10 raised power minus 3. And let's see what we'll get above. So we'll write dy by dx as f of x plus 0.001 minus fx divided by 0.001 if I take this value of delta x. Correct? So this step to this step it'll be this. Okay. Now what is the function? It is x cube. So what is the function's value at this? It is x plus 0.001 whole cube minus fx, that is x cube divided by 0.001. Okay. So far it's clear to everyone?
So why did you take cube over here?
Sorry, why did I take?
Cube.
Because that is the function ना बेटा, यहाँ पे देखो function क्या define किया मैंने, ना
Yes.
cube define किया. किस function के लिए मैं rate of change निकाल रहा हूँ? ये वाले function के लिए ना.
Yes.
Okay. So now tell me what I can do further. I can expand this using the formula a plus b whole cube.
Yes, sir.
Right. So this formula is correct. All of you are familiar with this, right?
Yes, sir.
So let's expand the numerator. So what it will become? It will become x cube plus 3x square into 0.001 plus 3x into 0.001 squared. Okay. So you'll have to write this term like this. Okay. Plus 0.001 whole cube. So this becomes just this term minus x cube, the whole thing divided by 0.001. Okay. So next step, see what happens. X cube cancels out. Okay. So I get 3x square into 0.001. Okay. Plus 3x into, now this will become how much? 0.00.
5 zeros and 1.
0, 1.
And we just divide all three terms by 0.001.
We'll do that now. We'll do that. Okay. So this will become how many zeros now? 8
zeros and 1.
Okay, something like this. Okay. Now this whole thing divided by 0.001. Okay. So now let's see how much it is giving us. So if I take 0.001 common in the numerator, give me 3x square plus 3x into 0.001 plus 0.000001. Correct? This is going to give me 3x square plus 3x into 0.001. Okay. So this is the instantaneous rate of change I'm getting. Okay. Now I can say that this is reasonably close to 3x square. Is this valid?
Sir.
No?
Sir.
Yes,
It's
sir.
reasonably close. Okay, I can say that. Okay.
Yes.
Now let's take a different value. Suppose I had taken the suggestion that delta x is something a little bit more interesting. Like let's say it's 10 raised to minus 5. Okay. Then see what this would have become. Dy by dx would have become x plus 10 raised to minus 5 cube minus x cube divided by 10 raised to minus 5. So this would have been x cube plus 3x square into 10 raised to minus 5 plus 3x into 10 raised to minus 10, okay, plus 10 raised to minus 15 minus x cube, the whole thing divided by 10 raised to minus 5. So if I take 10 raised to minus 5 common in the numerator, I would have got 3x square plus 3x into 10 raised to minus 5 plus 10 raised to minus 10 divided by this. So I would have got 3x square plus 3x into 10 raised to minus 5 plus 10 raised to minus 5 whole square. So you notice a pattern. Okay. When I'm taking, here I've taken dx or delta x equal to how much? 0.01, 0.001. So I'm getting this. Here I've taken delta x as 10 raised to minus 5. So now, for example, if I had taken, you can suggest that if I had taken delta x as 10 raised to minus 20, what I would have got dy by dx as? I would have got it as 3x square plus 3x into 10 raised to
10 raised to minus 20.
Okay. Plus 10 raised to minus 20 ka whole square.
40.
Okay. So you can see the smaller the value of delta x I'm taking, na, the closer I'm coming to 3x square. Like this one is much closer to 3x square than this one is. And this one is much closer than this one is. So it's following a pattern. मैं जितना छोटा लूंगा dx का delta x का value, the closer I'm coming to the actual value of 3x square. Got the point now?
Sure.
Yes, sir.
So now I can say that, okay, this I can approximate as 3x square. Okay, This I can approximate as 3x square. Okay, but the moment I take delta x tending to 0, okay, my dy by dx will actually become an exact value of 3x square. It will no longer be approximately, it will be exact. You understanding the point now? Because this second and third number here, it will be unimaginably small. It's not like it's 10 raised by minus 50 or 10 raised by minus 100. It's much smaller than that also, because it's tending to 0.
There will be a point where we will get the 3x square as our answer, the rate of change.
Yes, yes. I mean, so okay, so that is the whole concept of differentiation. Okay, that is the concept of differentiation, that we are able to calculate this rate of change for such a small interval that your delta x is not 10 raised by minus 2 or 10 raised by minus 3 or 10 raised by minus 5 or minus 10, but it's unimaginably small. It's
So
tending to 0.
What will happen if the value goes beyond that value of delta x? We no longer we got during that we got the rate of change is 3x square. Delta x goes beyond that.
Beyond कैसे जाएगा बेटा? It's tending to 0 ना. So it can't go beyond ना. You understanding the point?
Much more.
The whole point is it's tending to 0 now. Okay.
Sir, so in questions like these, can we like instead of writing really big values like 10 raised to minus 5 or anything, can we just write delta x?
Yeah, so we'll come to that also. In fact, we'll see that differentiation will give us a direct formula from which we'll get 3x square. So we will also not be substituting this limit at all. Okay. But this is to show you actually that how that value 3x square comes. Understanding my point?
Yes, sir.
Okay. So just make a quick note of this. Okay, then we'll see another example.
So I have a question. How do we know what value of delta x are we supposed to take to get the accurate answer?
That is the point. We are not supposed to take any value. What we are supposed to do is we are supposed to solve for this when it is tending to 0. See, these values were just examples for you. You're understanding my point, beta?
Okay, sure.
Sir, can you please explain the second step?
Sorry, which one? The
second step, x cube plus bracket में 3x square plus 10 raised to minus 5 वाला.
So this is just the expansion of this formula, na? A plus b whole cube. See, I've written it above. A cube plus 3a square b plus 3ab square. So your a is how much? X. Your b is 10 raised by minus 5. So just expand it by this formula to get this.
Okay, sir.
So this whole term, na, from here to here, it is this only, na? A cube plus 3a square b plus 3ab square plus b cube, where a is x and b is 10 raised to the power minus 5. So you're getting these terms. Okay, and the minus x cube is there at the end because this term is there.
Sir, when the exams come, so will there will be quick revision for this?
बेटा अभी एग्जाम का क्यों टेंशन ले रहा है? सेकंड लेक्चर है ना आज तो.
हाँ सर.
अभी एग्जाम का मत सोचो. Just think you are learning something new, ना?
Okay. Okay.
When exam comes, everything will do properly. Don't worry.
Okay.
Sir, can we take any value at 0 in the place of 0 for limit?
So now see, the problem is now what happens if we take directly 0. So let me explain that. Okay, so we have got this function which was x cube, and we have defined dy by dx as limit delta x tending to 0. Okay, f of x plus delta x minus fx divided by delta x. Okay, so when I substitute fx as x cube, this further solves out to be x plus delta x cube minus x cube divided by delta x. Okay, so till now we had taken some suggested values of delta x and solved, so that was fine. Now let's come to your question. What happens if I directly substitute delta x as 0? So see what will happen here. If you put delta x as 0, see what will happen in the numerator.
Sir,
What will be the numerator?
Not defined, no?
It will be 0 by 0, no? So it is undefined. So that means we can't substitute 0
if we
directly.
take 0, then slope to बनता ही नहीं है.
Sorry? If we take 0, then?
If we take delta x as 0, then we don't get the slope only.
Why we don't get the slope? No, because you see that what is the numerator then? It's
So
x cube minus x cube is 0 and the denominator is 0. So we cannot define it. No? And the reason is very clear why we can't define it. No? Because we cannot say what is, for example, the instantaneous speed in an interval of 0 seconds. No? It has to be a small interval tending to 0, but it should not be equal to 0. You're understanding the point?
Yes, sir.
Okay, so here we cannot substitute delta x directly as 0. But what we can do is we can expand this using algebra like we did earlier. So we can continue with the condition that limit delta x tends to 0, but we can expand the numerator as x cube plus 3x squared delta x plus 3x delta x square, okay, plus delta x cube minus x cube divided by delta x. So we still have a problem if we make delta x equal to 0, because still the numerator by denominator will become 0. So we have to solve this a little bit further. So first thing is we cancel x cube and we take delta x common. So now see, we are coming to a very critical step. 3x square into delta x, okay, plus 3x into delta x square plus delta x cube divided by delta x. Okay, so that is becoming, now take delta x common. Okay, if I take delta x common in the numerator, this will become 3x square plus 3x into delta x plus delta x square, okay, divided by delta x. Now the next step is very critical. See what I know about delta x, that delta x is tending to 0, but definitely delta x is not equal to 0. So as long as it is not equal to 0, I can cancel these two. Understood the point? In maths, a by a is equal to 1 as long as a is not equal to 0. Okay, if it's 0, then it's not defined. So it has to be non-zero. So here also what it is, delta x is a non-zero quantity. It's tending to 0, but it is not equal to 0. Okay, so delta x tends to 0, but at the same time, it is non-zero. It is as close to 0 as you can imagine, but it's not exactly equal to 0. So it is legitimate operation to, or it's a legal operation to cancel delta x and delta x, or to say that delta x divided by delta x is 1. So the moment we do that, now we've got the condition that limit delta x is tending to 0, 3x square plus 3x into delta x plus delta x square. Now here we can say that, okay, delta x is tending to 0. That means this whole term is tending to 0. This whole term is tending to 0. So what we are left with? We are left with 3x square. So that becomes the value of dy by dx. This is the rate of change for y equal to x cube. So already you can see that we have simplified our method a little bit. We are not taking some suggested value of delta x like 10 raised power minus 20 or 10 raised power minus 5 or something like that. We are just going along with delta x only. But in the final step, we are taking delta x tending to 0 after we have solved this with some algebra. Is it clear?
Yes.
Okay.
Yes, sir.
Okay, so now let's understand another example of the same thing. If I had y is equal to x square, can you calculate dy by dx by using the same method? Use the definition of dy by dx as for this function. Okay, try this yourself, see what you get. Yes, once that is correct. Okay, but I want you to actually calculate it by using the limit method. Yes, Vatsal, that's correct. Very good. Okay, so let's look at this. Okay. So the function is x square. Okay. So the instantaneous rate of change should come by solving this definition or this condition. So substitute the function as the whole square function. So this is x plus delta x whole square minus x square divided by delta x. Now just expand it like we did for x cube.
dy by dx is
yes. How much is coming?
2.
Okay, so cancelling of the x square, you can see that we are left with 2x delta x plus delta x square in the numerator divided by delta x in the denominator. So again, I can take delta x common in the numerator. I can write this now as 2x
2x
plus
plus
delta
delta
x.
x.
So now this thing delta x is negligible compared to 2x. So this will become how much? It will become 2x. So for this function, becoming this. Okay. So when we calculate differentiation by this method, by solving this limit, okay, this is called instantaneous rate of change. By solving the limit method. Okay. This is called method of limit. Okay. Okay, so already you've seen without that much effort, we have learned how to find the instantaneous rate of change for two functions just today. We have seen that for y equal to x cubed, we just saw that the instantaneous rate of change is given by 3x square. For y equal to x square, we are seeing that the instantaneous rate of change is equal to 2x. Okay. Now let's interpret these results geometrically. Okay. So
sir, do we have a formula for that?
Yeah, we have a formula. Eventually, we'll see that also. But today, I'm not interested in that formula. I'm more interested in the interpretation of this. So let's understand that. Okay. So graphical interpretation of instantaneous rate of change. Dy by dx. Okay. So when we are defining for a function, we are defining the instantaneous rate of change as this limit. Let's see what that gives us in terms of the graph. Okay. So suppose I apply this definition of dy by dx or instantaneous rate of change. Instead of applying it to some formula of a function like x cube or x square, etc. Instead, what is given to me is not a formula, but what is given to me is a graph. Okay. So the graph of the function is something like this, let's say. This is the graph of the function. And I want to find out the instantaneous rate of change for this particular point x, which has the corresponding value of the function, which is fx or y equal to fx at this point. So what do I mean by this thing, this limit? So let's understand that. So to understand this limit, since delta x is tending to 0, I'll again have to zoom in as much as I can. Okay. And tending to 0 means actually zooming in is also not good enough because I have to go infinitely close to this point. But anyhow, let's zoom in here and see what we get. Okay. So this point has an x coordinate of x and a y coordinate of fx. So what would be the point which is my x plus delta x, but delta x tending to 0? It would be this point. So this interval here between this and this interval in my new language of calculus, this interval is no longer a delta x, it is a dx, where dx is equal to delta x tending to 0. It's a limit that delta x is tending to 0. Okay. So correspondingly, what is my dy? It is this quantity here.
D is change, right?
Yeah. Okay. But very small change. Now, d is very small change. So dy is delta y tending to 0 because delta x is tending to 0. Okay. And now if I join these 2 points with a straight line, you can see that the slope of that straight line will be nothing but the instantaneous rate of change. So if you just imagine that we have joined these 2 points, okay. So when I zoom out, you can see that these 2 points have merged. If I take delta x tending to 0, they've merged perfectly. So remember earlier also we had discussed when this is a perfect tangent line, when those 2 points have exactly merged. So when they will perfectly merge, when the delta x is tending to 0, it's as close to 0 as you can imagine it to be. Okay. So the graphical interpretation becomes that it is the slope of the tangent drawn at x equal to x. And now what is the tangent? The tangent is the line joining the point x equal to x with x equal to x plus dx, where what is dx? Dx is equal to limit delta x tending to 0. It's a change in x that is so small that it's tending to 0. So therefore you can see that the points are merged. They are not almost merged, they are actually merged now because we are taking delta x tending to 0. So it gives us an exact method of calculating this slope. What the point now?
Yes, sir.
Yes. Any question? Okay, so for today, we're just learning the definition of what is instantaneous rate of change. This is the definition that dy by dx is the limit delta x tending to 0, change in y upon change in x. And what does that definition mean in terms of the graph? It means it is the slope of the tangent. Okay. And of course, we have seen 2 examples that if the function is x cubed, then dy by dx is given by the formula 3x square. If it is x square, it is given by the formula 2x. Okay. Now, before we conclude, we'll see one special case of instantaneous rate of change. That is, if the function is linear. Okay, so what is a linear function? This type of function. Y is equal to mx plus c, where m and c are constants. Okay. Then,
yes, sir.
Whether we calculate instantaneous rate of change or we calculate average rate of change, okay, both are equal to the slope of the line. Okay, because a linear function has a straight line graph. The graph of a linear function is a straight line. So that becomes a very simple case. So we don't need to apply any complex formula or anything for instantaneous rate of change then. We just know whatever is the slope of the line, that will become the instantaneous or the average rate of change. So for example, if we have got one particular straight line which has a positive slope like this one. So just as an example, let's take y is equal to 2x plus 3. So we will see that this line, it has a slope or tan theta equal to plus 2. Okay. So now we'll see that both the instantaneous rate of change, that is also equal to plus 2, and the average rate of change between any 2 points, that is y2 minus y1 upon x2 minus x1, that is also equal to plus 2. Okay. Similarly, if we have another example of a straight line which has a negative slope, so this time let's say we have straight line like this one. So in this example, let's say the straight line is equal to y equal to, let's say, 4 minus x. So we can see the slope is equal to minus 1. Okay. So this is an obtuse angle. That's why it's making. So tan theta equal to slope equal to minus 1. So that means whether we are calculating dy by dx or we are calculating delta y by delta x, both will be equal to minus 1. So that is the property of a linear function. So for any linear function, average rate of change equals to instantaneous rate of change equals to the slope, or basically m, for the linear function y equal to mx plus c. So this is a unique property that the linear function has. Okay. Other functions which are non-linear like x square, x cube, or sin x, or tan x, or any other function will not have this property. It's only one type of function. Yes.
In terms of speed, distance and time, it just basically means that there's uniform speed the entire time.
Yes,
We're
there's
calculating
uniform
the
speed the
average
entire
speed, and the instantaneous speed is also same at every single time interval.
Correct. Average speed between any two intervals of time or any two instants of time will be the same as the instantaneous speed at any particular point of time, which will be equal to the total distance divided by the total time for the journey.
Yes, sir.
Okay, but that only happens when the speed is uniform, and whenever the speed is uniform, our distance time graph will be a straight line.
Yes, sir.
Whereas if you think reverse of that, if our speed is non-uniform, then definitely our distance time graph will not be a straight line.
It will be a curve.
It will be a curve. So whenever our graph is non-linear or it's not a straight line, then this statement cannot be held true. No?
Yes, sir.
Okay. And that we've already seen for the example of x square and x cube above, that the slope at every point is different because the value of 2x is different at every point, or the value of 3x square is different at every point.
Yes, sir.
So that's the idea. Okay, people, so hope this point of the difference between instantaneous rate of change and average rate of change is clear to all of you. It becomes same only in one unique case, and that is the case of the linear function. Otherwise, there are two different things which are calculated by two different methods. So instantaneous rate of change is dy by dx, and average rate of change is y2 minus y1 upon x2 minus x1. Okay, so with that, we come to a conclusion of today's lecture. So along with this, I'll be sending you a worksheet of few questions which are just based on direct definition and simple ideas. You just try out those questions before the next week, and of course do a revision of the class notes and everything. Okay, that's it for today, people. Wish you all the best. Yes.
Sir.
Thank you, sir.
Yes.
I just wanted to ask, sir, in that graph, how did you get the slope as -1?
It's not from the graph beta, it's from the formula of the line that is given. See, what is the formula of the line that I taken in the second example? Y equal to 4 minus x. Okay.
Yes.
So what is the coefficient of x here? It's -1.
Yes, -1.
So m का value कितना हो गया? -1 हो गया.
Okay.
Okay, so that is only the slope, no?
Yes, sir.
You understood? So that's how we got it as -1.
Okay, sir. And sir, we have to submit the homework on Discord, sir.
Yeah, by next week, no? Before next week's class, you submit the homework on Discord. Okay.
Okay.
I
Thank you.
haven't got the homework assignment yet.
I'll be sending it to you. I told you I'll be sending it on the group. Okay, after today's lecture. Yeah.
Thank you, sir.
Thank you, sir.
Okay. Okay, people. All the best.
Bye, sir.
Bye. Bye.